You wrote the book Something Deeply Hidden on the Mysteries of Quantum Mechanics, and a new book coming out soon, part of that Biggest Ideas in the Universe series we mentioned, called Quanta and Fields. So that's focusing on quantum mechanics. Big question first. Biggest ideas in the universe. What to you is most beautiful or perhaps most mysterious about quantum mechanics?
Quantum mechanics is a harder one. You know, I wrote a textbook on general relativity, and I started it by saying general relativity is the most beautiful physical theory ever invented. And I will stand by that. It is less fundamental than quantum mechanics, but quantum mechanics is a little more mysterious. So it's a little bit kludgy right now. You know, if you think about how we teach quantum mechanics to our students, the Copenhagen interpretation, it's a god-awful mess. Like, no one's going to accuse that of being very beautiful. I'm a fan of the many worlds interpretation of quantum mechanics, and that is very beautiful in the sense that fewer ingredients, just one equation, and it could cover everything in the world. It depends what you mean by beauty, but I think that the answer to your question is quantum mechanics can start with extraordinarily austere, tiny ingredients, and in principle lead to the world, right? That boggles my mind. It's much more comprehensive. General relativity is about gravity, and that's great. Quantum mechanics is about everything and seems to be up to the task. And so I don't know, is that beauty or not, but it's certainly impressive.
So both for the theory, the predictive power of the theory, and the fact that the theory describes tiny things creating everything we see around us.
It's a monist theory. In classical mechanics, I have a particle here, particle there. I describe them separately. I can tell you what this particle is doing, what that particle is doing. In quantum mechanics, we have entanglement, right? As Einstein pointed out to us in 1935. And what that means is there is a single state for these two particles. There's not one state for this particle, one state for the other particle. And indeed, there's a single state for the whole universe, called the wave function of the universe, if you want to call it that. And it obeys one equation. And it is our job then to sort of chop it up, to carve it up, to figure out how to get tables and chairs and things like that out of it.
You mentioned the many worlds interpretation, and it is, in fact, beautiful. But it's one of your more controversial things you stand behind.
Yeah.
You've probably gotten a bunch of flack for it.
I'm a big boy. I can take it.
Well, can you first explain it, and then maybe speak to the flack you may have gotten?
Sure. You know, the classic experiment to explain quantum mechanics to people is called the Stern-Gerlach experiment. You're measuring the spin of a particle, okay? And in quantum mechanics, the spin is just a spin. It's the rate at which something is rotating around in a very down-to-earth sense. The difference being is that it's quantized. So for something like a single electron or a single neutron, it's either spinning clockwise or counterclockwise. Those are the only two, let's put it this way, those are the only two measurement outcomes you will ever get. There's no it's spinning faster or slower. It's either spinning one direction or the other. That's it. Two choices, okay? According to the rules of quantum mechanics, I can set up an electron, let's say, in a state where it is neither purely clockwise or counterclockwise, but a superposition of both. And that's not just because we don't know the answer. It's because it truly is both until we measure it. And then when we measure it, we see one or the other. So this is the fundamental mystery of quantum mechanics, is that how we describe the system when we're not looking at it is different from what we see when we look at it. So what we teach our students in the Copenhagen way of thinking is that the act of measuring the spin of the electron causes a radical change in the physical state. It spontaneously collapses from being a superposition of clockwise and counterclockwise to being one or the other. And you can tell me the probability that that happens, but that's all you can tell me. And I can't be very specific about when it happens, what caused it to happen, why it's happening, none of that. That's all called the measurement problem of quantum mechanics. So many worlds just says, look, I just told you a minute ago that there's only one wave function for the whole universe. And that means that you can't take too seriously just describing the electron. You have to include everything else in the universe. In particular, you clearly have to interact with the electron in order to measure it. So whatever is interacting with the electron should be included in the wave function that you're describing. And look, maybe it's just you. Maybe your eyeballs are able to perceive it, but okay, I'm going to include you in the wave function. And if you do that, let's be, since you have a very sophisticated listenership, I'll be a little bit more careful than average. What does it mean to measure the spin of the electron? We don't need to go into details, but we want the following thing to be true. If the electron were in a state that was 100% spinning clockwise, then we want the measurement to tell us it was spinning clockwise. We want your brain to go, yes, the electron was spinning clockwise, right? Likewise, if it was 100% counterclockwise, we want to see that, to measure that. The rules of quantum mechanics, the Schrödinger equation of quantum mechanics, is 100% clear that if you want to measure it clockwise when it's clockwise and measure it counterclockwise when it's counterclockwise, then when it starts out in a superposition, what will happen is that you and the electron will entangle with each other. And by that, I mean that the state of the universe evolves into part saying the electron was spinning clockwise and I saw it clockwise. And part of the state is it's in a superposition with the part that says the electron was spinning counterclockwise and I saw it counterclockwise. Everyone agrees with this. Entirely uncontroversial, straightforward consequence of the Schrödinger equation. And then Niels Bohr would say, and then part of that wave function disappears. And we're in the other part. And you can't predict which part it will be, only the probability. Hugh Everett, who was a graduate student in the 1950s, was thinking about this, says, I have a better idea. Part of the wave function does not magically disappear. It stays there. The reason why that idea, Everett's idea, that the whole wave function always sticks around and just obeys the Schrödinger equation, was not thought of years before, is because naively you look at it and you go, okay, this is predicting that I will be in a superposition, that I will be in a superposition of having seen the electron be clockwise and having seen it be counterclockwise. No experimenter has ever felt like they were in a superposition. You always see an outcome, okay? Everett's move, which was kind of genius, was to say, the problem is not the Schrödinger equation. The problem is you have misidentified yourself in the Schrödinger equation. You have said, oh, look, there's a person who saw counterclockwise. There's a person who saw clockwise. I should be that superposition of both. And Everett says, no, you're not. Because the part of the wave function in which the spin was clockwise, once that exists, it is completely unaffected by the part of the wave function that says the spin was counterclockwise. They are apart from each other. They are uninteracting. They have no influence. What happens in one part has no influence in the other part. So Everett says the simple resolution is to identify yourself as either the one who saw spin clockwise or the one who saw spin counterclockwise. There are now two people. Once you've done that experiment, the Schrödinger equation doesn't have to be messed with. All you have to do is locate yourself correctly in the wave function. That's many worlds.
The number of worlds is
very big.
Very, very, very big. Where do those worlds fit? Where do they go?
The short answer is the worlds don't exist in space. Space exists separately in each world. So, there's a technical answer to your question, which is Hilbert space, the space of all possible quantum mechanical states. But physically, we want to put these worlds somewhere. That's just a wrong intuition that we have. There is no such thing as the physical spatial location of the worlds because space is inside the worlds.
One of the properties of this interpretation is that you can't travel from one world to the other.
That's right.
Which kind of makes you feel that they're existing separately.
They are existing separately and simultaneously.
Without
locations in space.
How is it possible to visualize them existing without a location in space?
The real answer to that, the honest answer, is the equations predict it.
Yeah.
If you can't visualize it, so much worse for you. The equations are crystal clear about what they're predicting.
Is there a way to get to the closer to understanding and visualizing the weirdness of the implications of this?
I don't think it's that hard. That wasn't that hard for me. I don't mind the idea that when I make a quantum mechanical measurement, there is later on in the universe multiple descendants of my present self who got different answers for that measurement. I can't interact with them. Hilbert space, the space of all quantum wave functions, was always big enough to include all of them. I'm going to worry about the parts of the universe I can observe. So let's put it this way. Many worlds comes about by taking the Schrodinger equation seriously. The Schrodinger equation was invented to fit the data, to fit the spectrum of different atoms and different, emission and absorption experiments. And it's perfectly legitimate to say, well, okay, you're taking the Schrodinger equation, you're extrapolating it. You're trusting it, believing it beyond what we can observe. I don't want to do that, right? That's perfectly legit, except, okay, then what do you believe? Come up with a better theory. You're saying you don't believe the Schrodinger equation. Tell me the equation that you believe in. Turns out, and people have done that, turns out it's super hard to do that in a legitimate way that fits the data.
And many worlds is a really clean.
Absolutely. The most austere, clean, no extra baggage theory of quantum mechanics.
But if it in fact is correct, isn't this the weirdest thing of anything we know?
Yes. In fact, let me put it this way. The single best reason, in my mind, to be skeptical about many worlds is not because it doesn't make sense or it doesn't fit the data or I don't know where the worlds are going or whatever. It's because to make that extrapolation, to take seriously the equation that we know is correct in other regimes, requires new philosophy, requires a new way of thinking about identity, about probability, about prediction, a whole bunch of things. It's work to do that philosophy, and I've been doing it, and others have done it, and I think it's very, very doable. But it's not straightforward. It's not a simple extrapolation from what we already know. It's a grand extrapolation very far away. And if you just wanted to be sort of methodologically conservative and say, that's a step too far, I don't want to buy it, I'm sympathetic to that. I think that you're just wimping out. I think that you should have more courage, but I get the impulse.
And there is, under many worlds, an era of time where if you rewind it back, there's going to be one initial state.
That's right. All of quantum mechanics, all different versions require a kind of arrow of time. It might be different in every kind, but the quantum measurement process is irreversible. You can measure something, it collapses, you can't go backwards. If someone tells you the outcome, if I say, I've measured an electron, its spin is clockwise, and they say, what was it before I measured it? You know there was some part of it that was clockwise, but you don't know how much, right? And many worlds is no different. But the nice thing is that the kind of arrow of time you need in many worlds is exactly the kind of arrow of time you need anyway for entropy and thermodynamics and so forth. You need a simple, low entropy initial state. That's what you need in both cases.
So if you actually look at, under many worlds, into the entire history of the universe, correct me if I'm wrong, but it looks very deterministic.
Yes.
In each moment, does the moment contain the memory of the entire history of the universe? To you, does the moment contain the memory of everything that preceded it?
As far as we know, so according to many worlds, the wave function of the universe, all the branches of the universe at once, all the worlds, does contain all the information. Calling it a memory is a little bit dangerous because it's not the same kind of memory that you and I have in our brains, because our memories rely on the arrow of time. And the whole point of the Schrodinger equation or Newton's laws is they don't have an arrow of time built in. They're reversible. The state of the universe not only remembers where it came from, but also determines where it's going to go in a way that our memories don't do that.
But our memories, we can do replay. Can you do this?
We can, but the act of forming a memory increases the entropy of the universe. It is an irreversible process also, right? You can walk on a beach and leave your footprints there. That's a record of your passing. It will eventually be erased by the ever-increasing entropy of the universe.
Well, but you can imperfectly replay it. I
Yeah.
guess, can we travel back in time imperfectly?
Oh, it depends on the level of precision you're trying to ask that question. The universe contains the information about where the universe was, but you and I don't. We're nowhere close.
And it's what computationally very costly to try to consult the universe.
Well, it depends on, again, exactly what you're asking. Like, there are some simple questions, like what was the temperature of the universe 30 seconds after the Big Bang? We can answer that, right? That's kind of amazing that we can answer that to pretty high precision. But if you want to know where every atom was, then no.
What to you is the Big Bang? Why did it happen?
We have
What-
no idea.
what-
I think that's a super important question that I can imagine making progress on. But right now, I'm more or less maximally uncertain about what the answer
You
is.
think black holes will help?
No.
Potentially?
Not that much. Quantum gravity will help, and maybe black holes will help us figure out quantum gravity. So indirectly, yes. But we have the situation where general relativity, Einstein's theory, unambiguously predicts there was a singularity in the past. There was a moment of time when the universe had infinite curvature, infinite energy, infinite expansion rate, the whole bit. That's just a fancy way of saying the theory has broken down. And classical general relativity is not up to the task of saying what really happened at that moment. So it is completely possible there was, in some sense, a moment of time before which there were no other moments. And that would be the Big Bang. Even if it's not a classical general relativity kind of thing, even if quantum mechanics is involved, maybe that's what happened. It's also completely possible there was time before that, space and time, and they evolved into our hot Big Bang by some procedure that we don't really understand.
And if time and space are emergent, then the before even starts getting real weird.
Well, I think that if there is a first moment of time, that would be very good evidence, or that would fit hand in glove with the idea that time is emergent. If time is fundamental, then it tends to go forever because it's fundamental.
Well, yeah. I mean, the general formulation of this question is what's outside of it? Well, what's outside of our universe? So in time and in space. I know it's a pothead question, Sean. I understand. I apologize.
Look, that's my life. My life is asking pothead questions.
Okay.
Some of them, the answer is that's not the right way to think about it.
Okay. But is it possible to think at all about what's outside our universe?
It's absolutely legit to ask questions, but you have to be comfortable with the possibility that the answer is there's no such thing as outside our universe. That's absolutely on the table. In fact, that is the simplest, most likely to be correct answer that we know of.
But it's the only thing in the universe that wouldn't have an outside.
If the universe is the totality of everything, it would not have an outside.
That's so weird to think that there's not an outside. We want there to be. We want there to be sort of a creative force that led to this, and an outside. Like, this is our town, and then there's a bigger world, and there's always a bigger world. And
because that is our experience.
Yeah.
That's the world we grew up in, right? The universe doesn't need to obey those rules.
Such a weird thing.
When I was a kid, that used to keep me up at night. Like, what if the universe had not existed?
Right. And it feels like a lot of pressure that if this is the only universe, and we're here, one of the few intelligent civilizations, maybe the only one. It's the old theories that we're the center of everything. You just feel suspicious. That's why many worlds is kind of exciting to me, because it is humbling in all the right kinds of ways. It feels like infinity is the way this whole thing runs.
There's one pitfall that I'll just mention, because there's a move that is made in these theoretical edges of cosmology that I think is a little bit mistaken, which is to say, I'm going to think about the universe on the basis of imagining that I am a typical observer. This is called the principle of typicality, or the principle of mediocrity, or even the Copernican principle. Nothing special about me. I'm just typical in the universe. But then you draw some conclusions from this. And what you end up realizing is you've been hilariously presumptuous, because by saying I'm a typical observer in the universe, you're saying typical observers in the universe are like me. And that is completely unjustified by anything. So I'm not telling you what the right way to do it is, but these kinds of questions that are not quite grounded in experimental verification or falsification are ones you have to be very careful about.
That to me is one of the most interesting questions. There's different ways to approach it, but like, what's outside of this? How did the Big Bang start? How do we get something from nothing? That's always the thing you're sneaking up to. When
Yeah.
you're studying all of these questions, you're always sneaking. That's where the black hole and the unifying, getting quantum gravity, all this kind of stuff. You're always sneaking up to that question. Where did all of this come from? So,
Yeah,
and I think that's
fair.
probably an answerable question, right?
No.
It doesn't have to be. So you think there could be a turtle at the bottom of this that refuses to reveal its identity?
Yes. I think that specifically the question, why is there something rather than nothing,
Yeah.
does not have the kind of answer that we would ordinarily attribute to why questions. Because typical why questions are embedded in the universe. And when we answer them, we take advantage of the features of the universe that we know and love. But the universe itself, as far as we know, is not embedded in anything bigger or stronger, and therefore it can just be.